every day that you see a real life superhero, do you? Well, in this video, we are going to be interviewing one. More specifically, we are going to be interviewing Jack Dongarra, should I say, Professor Dongarra. And he's a legendary computer scientist. More precisely, a pioneer in supercomputing. So, stay tuned for this video. Here we have Professor Dongarra, one of the legendary computer scientists in the world and one of the pioneers of supercomputing. He has been here from bare-bone beginnings of supercomputing. And I don't even know where to start from all of his awards. I can go on for hours and hours. From his hundreds of scientific publications to his Turing Medal. And not to mention, he's also a member of the National Academy of Science. It's a true honor, a deep and true honor to be with you here, Professor Dongarra.
It's a pleasure to be here.
Thank you very much for the time.
Well, it's a pleasure to be with you as well. It's morning here in Oak Ridge, Tennessee, where I live. I'm in my office in my home, and I'm happy to see you as well.
Thank you. So let's get started with some questions. First of all, how did you get interested in supercomputing?
Well, I was always fascinated by computers, and when I took my first job, I was at a research facility which had one of the most powerful computers at the time. And my fascination with looking at powerful supercomputers, I guess, started at that point. I was just finishing my undergraduate degree, and I found a passion for doing computing. And in that case, I was looking at one of the fastest computers, and I also found a passion in looking at high-performance computing, looking at the fastest computers that are available for scientific computations.
So I really just got inspired of how much data types and how much data you can work with all of these supercomputers.
Yeah, so supercomputers are called super because they do a number of things. They allow calculations to go on very rapidly, and they're able to process large amounts of data quickly. So both of those dimensions give rise to having the fastest computers. We need the fastest computers so that we can process a lot of data and do that processing to get great fidelity, great accuracy in the solutions. So we're looking for solutions to problems which require many computations over a short period of time, so that we can carry on with analysis.
So tell us, impressive things you have accomplished in the world of supercomputing. How have these advancements benefited scientists and technology?
Right. Well, supercomputers are used in many areas. They're used primarily to help us. One of the ways in which supercomputing touches all of us is in the weather forecasting. So supercomputers are used by weathermen to predict or forecast the future weather. So when we turn on the news and we listen to the weather forecaster tell us about what the weather is going to be tomorrow, in 2 days, down over the week period, that's all those projections, all of those forecasts are coming about because of simulation on a supercomputer of the weather. So that's probably the simplest way in which they touch most of us every day. So weather and climate forecasting are very important. Oil exploration is another one. Biomedical research. Think about developing new materials or new drugs. It extends to looking at financial risk analysis, banks, and also data monetary transfers. It looks at animation. So animation is done on high-performance computers,
You mean
supercomputers.
like graphics design?
Exactly. Yeah. So if you take a look at a movie, whatever your favorite movie is, look at the
Star Wars.
Star Wars is a good example of that. That was a movie that was generated in large part because of the ability of animation to carry out those very realistic looking scenes that we have. So high performance computers are used in many areas.
Mm-hmm. So you're saying that supercomputers are used to predict and to make simulations, complicated simulations, to be able to do things. Like, for example, VR. It has kind of the same concept, but except you actually experience it yourself. In VR, the whole point is like a video game. You experience what you cannot really do in real life. Same thing in supercomputers. The reason why you simulate it is because that's the whole point of simulation, is that you are not there, but you simulate it. For example, if it would be very dangerous, something very dangerous, like if we were to simulate an explosion, you cannot be there watching the explosion next to it if you need really very deep and very in-depth information about the explosion. You couldn't just be here in front of it or you die. So that's why you also need a simulation, because it's like if you were just the camera of a movie. You have no effect, you have no life.
Yeah, so that's absolutely correct. So we use supercomputers to help in doing many facets of our daily life to build better products. So the tire company Goodyear, they use supercomputers to make tires that we have on our cars. They're much more safe because of the design that's done on a computer. Companies like Boeing and the Airbus, they use supercomputers to design fuel-efficient aircraft. So they're doing a simulation of the jet engine, trying to build
a simulation of how the aerodynamics of their vehicle would work if they were to launch it.
Yes, well, exactly. And then also the engine itself needs to be very fuel efficient as well. So they can think of a model that you have of something like an engine. It could be a combustion engine, a car engine, and you want to change the parameters to get better use of the fuel that's going in. So they run thousands of simulations adjusting the parameters until they get the parameters that meet that specification of giving better quality. And that's been going on for a while. We use it to improve cars in terms of crash worthiness. So in the old days, they would take a car, build it, and then crash it into a wall and see what happened. Well, today, they don't do that very much. They build a simulation, they build a model of a car, they put it on the computer, and then they simulate what happens to that model if they crash it in the wall. And then they adjust the parameters on the model to get something that's better in terms of safety. And they do that on a computer. They can do it very quickly. And the end result of that is a car that has better ratings in terms of its ability to withstand crashes.
So can you tell us impressive things you have accomplished in the world of supercomputing? How have these advancements benefited scientists and technology?
Right. So I've been involved in a number of things that have been put in place. One thing that I've been involved in is in finding very accurate and very quick solutions to very simple but fundamental problems in science. So there are problems that come up in various areas of science. I develop algorithms to solve those common problems very quickly on supercomputers. So I'm involved in designing software and algorithms that will work on supercomputers for solving these very standard problems that come up in many areas of science. So that's one area where I've done my work. Another area is looking at standards for using a computer. So we use a computer, we write software, we have routines that carry out certain functions. And throughout my career, I've helped design the interface to many of those routines, which are really fundamental. Some of those routines deal with numerical computation. Other routines deal with message passing, more of the infrastructure that's needed to carry out the computations. And the third thing I've been involved in is in the analysis of evaluating how fast supercomputers are. So I've been involved in the performance and analysis of many of the high performance machines that we have today.
And how have these advancements benefited scientists and technology?
Well, the work that I've done, how they've advanced, they help advance science. They help advance science through scientists using the tools that have been developed, and those tools really form, in some sense, the way I think of it is a fabric on which we do our computations. They're the things that many different scientists draw on to carry out their computations. So many of the things that take place today are using software that I helped develop and put in place. And it's just making their job, the scientist's job, easier to help solve problems across a range of different computers. So I'm developing, in some sense, the basic infrastructure that's needed for supercomputers to work.
Right. So it's like if you had a programming language such as C++ or whatever coding language you want to take, and you'd use libraries, coding libraries, so that you not need to reuse and remake those libraries.
That's exactly right. So we help design those libraries, and as you say, they're portable. One can use them on different machines and in different applications to help scientists solve problems much more easier than if they had to develop those routines from scratch or for their own specific applications.
Okay. So first we did that question, now this. So what exciting developments are currently happening in supercomputing?
Well, supercomputers are always getting faster, and they're getting more powerful as a result. Supercomputers are used for many kinds of computations, and they're finding new areas where supercomputers can be, in fact, used. So supercomputers are used to drive some of the learning, some of the training that goes on with many of the artificial intelligence tools that we have today. So a tool that is just becoming very popular, ChatGPT. The training that goes on for ChatGPT was done on supercomputers. It was done on a special computer that OpenAI has to do that training. That training takes an enormous amount of time. They scoop up all of the internet. All of the data on the internet is used in that process, and then it's run through their supercomputer to do the training process. Deep neural networks come into play in doing that. And the result of that is the database that ChatGPT uses in terms of answering the questions that you might pose to it. So the back end, or let me say the front end of this process, takes an enormous...
The visual look.
Well, no, don't think of it as a visual look. Think of it as the training process, taking all of the internet and pushing it through filters, which refine things to the point where they can easily be sought out. And then when you ask a question, it goes to that database that's been created by GPT, and then is able to draw out the knowledge that's in the internet to help solve your query. And it can do that very rapidly. But the training process takes literally months to do on a supercomputer.
There are two questions. Was that I'm getting a little bit mixed up with this back end and front end. Because I thought in web development, when you make sites, front end was the visual look and back end was the processing. Okay,
so we can use that notion. So then the back end is the part where all the computations are done, and the front end is the interface that the user sees, right. And the user interfaces with that. So on the back end, we have this enormous computing device which scoops up all of the internet, all of that data, processes it with deep neural networks, and then produces a database which is drawn on by the front end to effectively come up with answers to the problems you pose.
Thank you. And so you're saying that ChatGPT is powered by a supercomputer?
Absolutely, yes. And it's powered by supercomputers on the back end, right? So the back end, the part where we scoop up all the internet and process it so that it's in a form that can easily be retrieved.
I think some people would be questioning how is it possible to take data from a supercomputer into our computers that are not a supercomputer.
Well, we're using the front end is an ordinary PC. It can be an ordinary PC. There's a web interface that makes your query. It goes out to the ChatGPT site, and then it draws on the database that was created by that supercomputer. So the supercomputer is on the back end doing the processing. That's done once, and then once we have it, it can be used for all the queries that come from that point on. Now that database will need to be updated, so it'll be refreshed at some frequency, but that's not done every day or every hour or every minute. That's done once in a while because it takes months of computing time to generate that database. So it's not something that's done very often.
So it's saying it's like if we were to do a basic mathematic thing, like, I don't know, 34 times 15, you have to put much more work in calculating it than actually saying the answer.
Yes, so it's a way to sort of think of it as pre-processing everything, so you can easily draw the answer out once that pre-processing is finished.
Thank you. So now, question number 4. How do you view the future of supercomputing, and how will it help us in different areas such as medicine, weather forecasting, and robotics?
Right. So supercomputers are going to be here, and they're going to be improving in terms of their speed.
Capacity and speed.
Capacity and speed are the two important things, exactly. And they're going to be improving as we go forward. That's just the nature of the technology. These supercomputers are used for many different
simulations and subjects.
So an example would be simulating the human heart. So the supercomputer can be used to do a simulation, and it could be used to look at the effects of various drugs on the heart. So we're not going to experiment by actually giving this to a person. We're going to simulate what happens if a drug...
Like I said, it's better because if you were to actually test on a human, it might not work, and you have to... Simulations is all about doing it on something that does not exist to make sure that it would work if you would actually do it on something that would
Exactly, exist. That's right. And we use supercomputers to help with climate modeling, where they're going to analyze the ocean, understand what the ocean response is to the changing climate. And from that understanding, we may be in a better position to see what our future might be if we don't limit some of the damage we're doing to the climate itself. So it's a way to, in some sense, foresee the future. I think of a supercomputer as a crystal ball. It gives us a way to analyze things that might happen in the future. Given the current conditions, we can see what happens. The weather is an example of that, but we also use it to look at creating new materials. We look at using it to map the universe, to try to understand where the universe was created, how old it is, what the potential impact of those things are. So those are all things that we can use a supercomputer for.
Thank you very much. And I believe that in medicine it is used to help against cancer.
Right? Absolutely, yeah. So new drugs are being studied to help with cancer. There's an example of a high-performance computer being used to analyze 120 billion DNA sequences and narrowing down the cause of an infant's liver failure to 2 possible genetic variants. And the result of that diagnosis that was effectively carried out by a supercomputer helped save the life of a baby. So, supercomputers have many, many ways in which they can be deployed and used. They of course, can be used to work in the medical area. They can be used to
in the robotic area and in the weather forecasting area. So exactly. Weather forecasting is when you're trying to simulate the weather and the climate moving all the way around, mixing with temperatures and the overall climate change. And robotics, I believe that it is used to test with robots digitally, numerically, without actually needing to make a robot, remaking it, maybe it breaks, remaking it, you just do it digitally, and then you can see, oh, will it work? Will it be fine? Will it be good enough?
Yes, exactly. And, we use the robots are trained. There's, again, this idea of.
Like AIs, you can use AIs
Exactly.
to train it.
Yes.
So, right, thank you very much. And can you share any interesting stories you have faced in your career that have taught you valuable lessons?
Oh, stories about valuable lessons. Well, my career is a long career. I've learned many things from many people. Going to school, I've learned basic algorithms and designs of how things can be constructed. I've learned how to do the programming. I've learned how to apply those skills to solving real problems that people encounter. I've learned from the best in some sense. I think about this Turing Award that I have, and just removing myself from that picture. I've learned so much from the people who have received the Turing Award. I've read their papers, studied their books. I've used their programming languages. I've written a few papers with previous Turing Award recipients, and now I'm in that same class of people who I have tremendous respect for, and it's hard for me to really get my head around the fact that I now have this award myself. So it's always a learning process. One never stops in terms of understanding new things and trying to sort out the best way to accomplish things. And I would recommend anybody that our education is something that goes on throughout our life. It's not something which we stop at a certain point. It's something which the formal training may end, but the education process goes on, and we use the skills that we've learned in our classrooms on a daily basis. So it's important to effectively very well we have to very well understand the basics so that we can apply them to the problems that we have.
So I've heard you said that other people had these awards, because I thought that Nobel Prizes or even awards in general could only be given to one person.
Well,
but you're saying that it's like the FIFA World Cup. It's FIFA World Cup 1972.
No. I was speaking of all the previous award winners. So every year the award is given out. And
so it's like you get a trophy for every year. It's not like just one trophy you alternate against each person. You have multiple awards of the same type that you give to each person each year.
Well, one person gets the award per year. They may give it to two people, but one person usually gets it, and it's only done once a year. And I was the recipient. I was the previous recipient, and the new recipient of the Turing Award was announced last month.
Actually, got it very lately.
He just received. That's right, and it's the person who was the creator of the not the internet, but Ethernet. Ethernet connects computers together. Ethernet is the wiring and the protocols we use to connect computers together. So his name is Bob Metcalf. He was the designer of that many years ago, and he did a number of other things, of course, but he was recognized for his achievements for that. The internet also, the people who designed the internet also received the Turing Award a number of years ago. And of course, that has had tremendous impact on almost every area of our life.
What advice would you give to kids who want to become scientists or engineers in this field of supercomputing, or even people in general?
Well, what I tell my students is usually the following. They should first follow their passion. Find the problem they feel passionate about, they feel excited about, and want to work on.
So the simulation that they want to work on. Like if I wanted to work on a car crash, that's what you should focus on.
exactly. So find something that they feel passionate about. Aim high. Don't try to solve simple problems. Try to solve complex problems.
Challenging
Challenging problems.
to like progress, because if you only stay with the same questions and the same level, you will never excel and you will stay like cement. You will
That's
stay
right.
stiff. So you have to always be on this moving river of education so that you don't stay stiff on cement.
Very well put. And the third thing I tell people is we're doing research, and research is something where we don't know the answer. So people should expect to fail. They should expect not to get to the solution every time. They should be expecting that their ideas may not work, and don't be discouraged by that. Continue and carry on with understanding so that you can overcome that, and eventually, hopefully, one would overcome those obstacles, and you'd be able to solve the problem. The fourth thing I suggest is that people network or work with colleagues, bounce ideas off of other people to try to understand what your colleagues may have solutions to a problem that you're encountering, and they may be able to help you solve it. And likewise, you may be able to help others in solving their problems.
So, but we have to still be very careful, because sometimes when we're trying to work on a project, people sometimes steal the idea from you.
Well, I don't worry about that. So I'm of a point where if somebody has a better way of doing what I'm trying to work on, and they want to steal it, they can go ahead and steal it, and that's fine.
So what do you think about it is that the whole point is to progress, no matter who did it or what did it.
That's right.
It's about progressing.
Yeah, if somebody is smarter than me, I'm happy to recognize that they're smarter, and solve the problem is fine. I'd like to be able to be the one that solves the problem, but that doesn't always happen. It's a research, so it's a research area. So I don't know the answer to the problem before I start. I'm going to be working on something where I don't really understand how we're going to come to a conclusion, and we may not be possible. And I like to work with other people to try to help understand and to drive us to a good solution to the problem.
And this is going to be one of the more interesting questions. What is the architecture of supercomputers, or I could also say high-performance computing? And right. Well, what is the architecture of supercomputers?
Right, the architecture is the way in which they're built up. Supercomputers are composed of today. They're composed of usually commodity processors.
That is the daily processors, right? Commodity processors. The ones that we have.
The ones that we have in our supercomputer, in our computers, desk computers.
That's commodity.
Right. Plus accelerators. And the accelerators are usually of the form of a GPU, or a general purpose graphical processing unit. So that GPU boosts the floating point ability. So we usually do computations based on numerical values. We want to have a way to process those numerical values very quickly, and GPUs provide us that mechanism. So we're based on a commodity processor, which has a number of cores in it, processors in it, and a GPU, which can boost the performance. And now we're going to build a supercomputer with thousands of those parts, put them together, assemble it, and connect them together using a interconnection mechanism to allow us to pass data from one point to another.
So the supercomputers, so they contain multiple servers, like big fridges that have many layers of chips, and in these chips we have CPU, GPUs, accelerators. Well, I think GPUs are accelerators, right?
Yes.
Yes, so the GPU is just the overall name for all of the other accelerators that obviously accelerate the processing and the right. So that's how it works, the architecture. And this other question is that what is CPU, what is GPU, and what is RAM?
Okay, so the CPUs that are commonly used come from basically two companies, Intel and AMD. So Intel's a computer company that makes processors. It's probably in your laptop or your computer that you have at home. AMD is a company which makes a similar product, It has the same instruction set. So the instructions are the things which execute on that computer. So they're compatible machines. I could take a program from an AMD processor and run it on an Intel processor without any problem. They have the same architecture. And we use that as the basis of writing our programs and developing our applications.
Thank you. And so the CPU, that's like the structure.
The CPU is the think of it as the
like the Swiss knife. It can do many different things, but it is a little bit limited.
It's the thing that's in control. It's the thing that executes instructions that you have given it, and it executes them today very rapidly. So, in a parallel programming world, that's where supercomputers are. You have to write a program which will execute simultaneously on thousands of processors, and maybe tens of thousands or hundreds of thousands of processors. So you have to orchestrate how those processors do their computation and communicate with each other. That's the basic way in which we do our programming. And we do that programming in C or C++, maybe Fortran. We do our communication using a layer or a fabric called MPI, Message Passing Interface, which allows messages to go between those processors. And the GPU is used to offload numerical computations that the CPU has. So think of a GPU as sitting there waiting for work. The CPU itself has the data and it sends it to the GPU, and then the GPU executes whatever it's been told to execute. And then
the CPU is like the receiver of your brain. It receives the information and then the GPU processes it. Then you output it onto the console.
So everything is controlled by the CPU. So think of the CPU as the one in control. It sends information.
The joystick.
And it comes back to the CPU. And now there are thousands of CPUs that you have to coordinate. So you have to write a program which will coordinate that. So think about the following. If you have a list of numbers that you want to sort, you can write a program that runs on one CPU to do that sorting. We can come up with many ways of doing it. So
you're saying that the CPU is like if we had a function and we wanted to put any argument in it. The CPU is what is the main object, and after the GPUs is like the arguments that you put in your functions.
That's right. But I was trying to get at the following point. On a parallel computer, you have to design something which will sort a list of numbers in parallel. So if you have 1,000 processors and you have a long list of numbers,
at the same time.
You're executing at the same time, but then we need a way to collect the information back and present this unified solution. So you may give them each a part of the data, and then they're going to work on their part.
That will form the full database.
So we might have to divide the database across all the processors, and then each of them gets a chunk of the data. They work on that chunk, and then they have to coordinate with other processors to put the information together, their information together. And that may be done in a tree-like fashion until we get to the top and get to the solution.
And do we use any RAM in supercomputers?
Well, so the computer is based on, at a very high level, it has two components. It has the processor and it has memory. So the memory is where the RAM is. The processing memory is random.
It's the temporary memory.
Well, it's the memory that the computer has. It's temporary in the sense that it's there for the length of the program. So it's the main part of where the data.
So it's just you use it for one specific task. You don't really use the information for the whole life cycle, for example. You don't use it for the whole program. You only use it for one chunk of it.
Okay. So there's different levels of RAM. There's different levels of memory. So there's the primary memory, which is used throughout the course of the computation. And then there's more temporary memory. Sometimes we call that cache. So we move data from memory into this cache, which is also memory. but it's much smaller. It's smaller and faster. It moves data faster. And then we think of, in the simplest case, the processor. So there's a large pool of memory, there's a small amount of cache, and then the processor. Moving data from memory, the large pool, to the processor is very expensive. So we put it in the cache. We put it in the smaller amount, smaller, faster place, and we hope that we can reuse the data. So there we're going to be reusing it. It's very temporary, and it works almost automatically. We don't have to control it directly. And
So we use so we use the CPU and GPU for large-scale tasks, and the RAM is really just a quick component that we use for quick calculations.
well, that's not quite what I was saying. So there's a large pool of memory which has an enormous capability, and then there's a smaller pool which is temporary, faster, and we can do the computations very rapidly with this cached memory, and that is used in many computations.
Thank you. So, how can supercomputers contribute to solving significant problems like climate change or advancing medical research?
Well, again, it comes down to doing a simulation. So we need to construct a simulation. We need to construct a mathematical model of whatever we're trying to understand. So we need a mathematical model of the weather or the climate or whatever the thing we're trying to model. So we come up with a set of equations which can describe how the weather progresses. So given some initial conditions, what the weather is right now, it'll predict what's going to happen in the next 4 hours. So that's the model. And then we put that model on our computer. That is, we translate the equations into a program that carries out those equations and evolve the story from what the weather is now into what the weather will be in the next increment of time, whatever that increment is. And the computer then goes through that simulation, going from the first point to the prediction very quickly, and then it can extend that to further points into the future. And that's what the simulation helps do. It helps push the solution to a further state.
Thank you. So finally, can you tell us about your current projects and what you find most exciting about the future of supercomputing?
Well, we're trying to design algorithms that run on the fastest computers. The new computers coming out are just being created. That is to say, the hardware is just being put in place. And now, when they turn on that hardware, they need to start using it for doing scientific computations. So we want to be in a position where we have the basic software ready for that computer when it starts running. So that's one of the things we're doing today, is designing software and algorithms that will run on the fastest supercomputers, these machines that we're calling exascale computers.
Thank you very much. I have one last question. Is that we're getting at the end of this introduction. Would you want to add anything more to this conversation or not?
Well, I would just say that high-performance computers are useful for all of science. Science today is driven by simulation, so we need the fastest computers to do the best science. We can push science forward if we have those computers, and we should invest in looking at high-performance computers for helping us with that scientific discovery. Many areas of the country, many countries are looking at different ways of purchasing or putting in place high-performance machines to help them solve their most challenging problems.
Thank you.
Thank you so much for this interview.
Just a quick conclusion.
Yes,
before we end the video, is that this video we learned about supercomputers, what do we use them for, and what are the components that we have inside. And just before we wrap up, I just had two questions for myself, is that, so you mentioned that we use commodity chips. My question was that, don't we use specialized chips for our supercomputers?
So today, most supercomputers are based on commodity processors. processors from Intel or AMD, and GPUs from companies like NVIDIA or even AMD or Intel. They also make GPUs. And we buy those chips because it's very expensive to design special purpose chips. You can design them, but they're very expensive. So we're driven to commodity processors because of the cost and potentially the high performance. So that's why
So they really just use it for the quantity because it's very expensive, you're saying. So in supercomputers, you really just worry about the quantity, whether not really qualities.
Well, it all comes down to cost in the end. We have to buy the fastest computers that we can with the money that's available to us.
The budget.
So the budget really dictates the kind of computer that we can buy. We want computers to be very, very fast, and we want them to be very inexpensive. Those are the two things that are in opposition. And if we build our own chips, it's very expensive, and we may not get a product which is better than if we assemble those commodity.
And I had a last question, a final question. So you were mentioning about C++ and C. So C++ is mainly used for embedded systems, right?
Well, no, actually, we use C++ as the main programming language for our simulation. So C++ is a language which allows us to express the program or the algorithms or the applications in a form which makes it easy to change and modify and move to different situations. So C++ is probably one of the languages that's most often used. C is also used. Some Python is used. Maybe Fortran. There's a whole collection of languages. The language itself is used again to express how we're going to be solving the problem, and we want to have the best way of expressing it because that minimizes our time.
Right. Thank you very much.
Well, thank you very much for this interview. That was very interesting.
You're an inspiration to the youth and to other scientists around the world. And thank you, contribution to science.
Thank you so much.